Hi everyone. So today I'm going to talk to you a little bit about the differences between proprioception and neuromuscular control. Just to review a little bit of what Dr. Flanagan spoke of in his functional training presentation, this diagram shows proprioceptors relaying information over to the central nervous system. The central nervous system then sends signals to the muscle to create an action. In this diagram, the left side represents proprioception, and the whole diagram represents neuromuscular control. There are two ways to measure proprioception: joint reposition error and passive movement. In both ways, the subject can't see or hear what's happening. In the reposition error test, the subject starts in a neutral position, and then the investigator takes their arm to a reference angle, so let's say 30 degrees. Then they're brought back to the neutral position, and the subject is asked to go to what they think 30 degrees is. And remember, they can't see or hear, so they don't have any cues of where to stop. They just have to feel where 30 degrees is. Once they get there, the investigator takes the difference between the reference angle and where the subject went to, what angle the subject went to on his or her own. In the passive movement test, the subject is laying in a neutral position, and then you passively start to move the joint and have the subject signal when they first detect there's going to be a movement. Another topic that Dr. Flanagan spoke about was if proprioception could be trained. He discussed that athletes have better proprioception than non-athletes because they have certain genetic gifts. There are studies that say proprioception can be trained, and there are others that say it cannot be trained. And a finding that keeps being seen in proprioception studies is that fatigue leads to more proprioceptive deficits. And this leads me to the article that I looked at entitled Proprioception and Neuromuscular Control of the Shoulder After Muscle Fatigue. This study was conducted out of UNC Chapel Hill and is published in the Journal of Athletic Training. The first sentence states, quote, "Since proprioception is a component of neuromuscular control, the two terms are often used interchangeably and incorrectly," unquote. So in this article, proprioception is the variation of the sensory modality of touch that encompasses joint movement and joint position. So it's similar to what Dr. Flanagan said about the proprioceptors, since they collect information about the joint movement and about the joint position and then relay it to the brain. The article also says that neuromuscular control is the unconscious motor efferent response to afferent sensory information. So basically, it's just the response to the information from the proprioceptors to signal that muscle action. Before beginning their own study, the researchers looked at the other studies in the topic of proprioception in the shoulder. They found that there were a lot of studies looking at proprioceptive deficits, but there were only 3 that studied the effect of fatigue on shoulder proprioception. In those studies, the researchers all concluded that fatigue affects sensation of joint movement, it decreases athletic performance, and it increases shoulder problems related to fatigue. With all of this research in mind, the purpose of the current study was to see how muscle fatigue affects shoulder proprioception and neuromuscular control. There was a focus on afferent proprioceptive feedback and efferent neuromuscular response. And by focusing on this, the researchers can look at how fatigue affects proprioceptive feedback, therefore how it affects neuromuscular control of the shoulder. The researchers took 32 college students, 16 males and 16 females. The males were 20 to 22, about 138 to 222 pounds and 5'9" to 6'1" in height. The females were 19 to 21 years old, about 108 to 138 pounds, and between 5'2" and 5'6". They were all physically active with no history of shoulder problems, and they were split into two groups, an experimental and a control group. The experimental group performed 3 different tests. The subjects volunteered to go to 2 testing sessions. One was the proprioceptive testing procedure, which was the active angle reproduction test, and the other was a neuromuscular control procedure, which was the single arm dynamic stability test. The order of testing was counterbalanced, which meant that half the subjects performed the active angle reproduction test first, and then the other half performed the single arm dynamic stability test first. And then before any of the testing, all subjects did a 2-minute warm-up activity using just the upper body on an ergometer, and then after that warm-up activity, they pre-tested using either the active angle reproduction test or the single arm dynamic stability test. The active angle reproduction test was measured with an isokinetic dynamometer using an active reproduction of the joint position. The subjects are laying flat on their backs with their arms secured at a 90-degree angle, as shown in that picture. The subjects' dominant arms were secured with an air splint. They were blindfolded, and they wore headphones to take away any cues. Before this test, the machine was calibrated at 0 degrees of the subject's shoulder rotation. The investigators manually rotated the shoulder at different speeds to one of 3 reference angles. Those were 30 degrees internal rotation, 30 degrees external rotation, or 75 degrees external rotation. They changed the speeds that they were moving to these reference angles at to prevent the subject's anticipation. After the reference angle was established, the subject was then asked to reproduce the angle. The investigators set a standard speed to make sure the motion to reproduce the angle was not restricted. So when the investigators were moving the subject's arms to those different reference angles, they were going anywhere from 1 degree per second to 5 degrees per second. When they asked the subject to reproduce that angle, they set the speed at 300 degrees per second. Once the subject hit what they thought was the reference angle, the investigators then calculated the absolute error by calculating the difference between the reference angle and the angle reproduced by the subject. The single-arm dynamic stability test was measuring neuromuscular control by calculating the sway velocity. The sway velocity is the measure of amplitude divided by time, and as we know, the amplitude is the distance in degrees traveled away from one's center of gravity, and time represented the duration of the trial. The subjects were in a single-arm push-up position with the dominant hand in the center of the force plate and the non-dominant hand on the small of the back. They had their eyes closed, and their feet had to be in the center of an unstable multi-directional platform, and each trial lasted 10 seconds, and they did 3 trials with 30 seconds rest in between. The subjects tended to fall during this test, and they defined a fall in 2 ways. Any type of touchdown to help stabilize, so if their non-dominant hand went down to the force plate, or their foot went off that unstable platform, or if the subject left the force plate completely. If this happened, then the test would stop automatically. And any fall meant that if it affected the sway velocity score, because falling increases the base of support. After the pretest, the subjects performed the fatigue protocol, and this was when they used continuous concentric internal and external rotation exercises, and they're asked to do this until they reached fatigue. And that was defined as performing 3 consecutive repetitions at 50% of the maximum peak torque of external rotation. Immediately after this fatigue protocol, subjects went on to the post-test, which was the pre-test procedure. Then the subjects were given 1 week between the 2 tests, and when they came back, they did the remaining testing protocol. So if they did the active angle reproduction test the first time, they would come back to do the single arm dynamic stability test the second time. So really quickly, before I get into the results, I realized I forgot to mention that the control group did the same exact tests as the experimental group, but instead of performing the fatigue protocol, the control group was inactive for 5 minutes. So, keeping that in mind, when looking at the shoulder proprioception results in the bar graphs to the right, there is a significant difference between the pretest and post-test values for the experimental group, but not a significant difference for the control group. In the single-arm dynamic stability test results in that table to the left, there wasn't a significant difference in pretest and post-test falls for the control group, but there was a really big difference in the falls after fatigue in the experimental group. So what does this all mean? The results show that fatigue decreased proprioception of the shoulder as measured through sensing the joint position. The explanation the article gives is that the muscle mechanoreceptors are probably the most important in getting a sense of the joint position. Because the muscle spindles detected a change, that information was relayed to the central nervous system. One of the reasons that stuck out to me for why fatigue decreased proprioception was that the fatigue protocol not only affected the shoulder muscles, but it also affected the central nervous system. The investigators did say that there's not a reliable way to measure all of this, but it is a definite possibility. The neuromuscular control results showed that there was no significant effects of fatigue on neuromuscular control when assessed by the sway velocity. The neuromuscular control needs afferent proprioceptive feedback from peripheral mechanoreceptors. This feedback is needed to produce signals such as reflexes and balance. And the fatigue of the mechanoreceptors can affect the co-contraction of the antagonist and agonist muscles of the shoulder. And this makes it difficult to stay in that one-arm push-up position. The investigators do say that there needs to be more research to see if and how fatigue affected neuromuscular control in this situation. So one of my favorite parts of the article was that it discussed the clinical significance of the results. Now, since fatigue delays proprioceptive feedback from the shoulder to the brain, neuromuscular responses could also be delayed, which could lead to a shoulder injury. Then, if someone can't recognize a joint position, or more importantly, the extremes of a joint position, there could be an injury from that increased mechanical stress. So if someone struggled with the active angle reproduction test and couldn't find that reference angle, they could also have trouble finding the extremes of their joint positions and get injured. Then the decreased proprioceptive sense due to fatigue could lead to a performance decrease. And we know that a performance decrease could also lead to injury. Finally, the article discussed how rehabilitation programs should include an endurance training element to them for dynamic shoulder stabilizers. And even if it's not for rehabilitation, increasing shoulder stability is always a good way to prevent shoulder injuries. So, to conclude, the results show decreased proprioceptive feedback after muscle fatigue, but the effect of fatigue on neuromuscular control was inconclusive. This shows that additional research is needed to really understand the effects of fatigue on both proprioception and neuromuscular responses. Thank you guys for taking the time to listen to my presentation, and have a great day.